Alrighty, everyone. So let's go ahead and let's get on started. So just a few things. This theory quiz review is entirely unofficial. I'm a TA for the course. I'm a grad TA for the course. But this isn't overseen or sanctioned by anyone. I'm just doing it because I don't have the free time. But I'm doing it because I just want to help you guys on this theory quiz. So if you're watching this and expecting to ace the theory quiz, I don't know. I don't know what's on the theory quiz. I don't know what to expect. What I have done is I've spent the past 2 days going through Dr. Hossain's lectures. And by going through his lectures, I've gotten some questions for you that he asked you in class. I have a lot of math questions. And by a lot, I mean like 4. I mean, anything more than 1 is a lot of math questions for me because I was doing them earlier just to make sure I could like explain them correctly. And I apparently forgot how to cross multiply and divide, but we fixed that. So it's great. So let's just kind of dive on in. So there are 4 labs total. On this upcoming theory quiz, you're going from isomerization all the way until the end of lidocaine. The good part about this theory quiz is that there is no NMR. So HNMR, you do not have to worry about. You are responsible for IR and gas chromatography and those things from the Ester lab. So keep that in mind. While there are 4 labs on this theory quiz, isomerization and beta-carotene, they cover very similar topics in terms of TLC. So the first thing I'm going to do here is just cover TLC as a whole. If you have any questions at all, feel free to interrupt me, private message me, unmute yourself, whatever makes you feel comfortable. The whole point of this session is for you guys to get the maximum out of it. So let's just kind of start with what chromatography is. So chromatography, which feels like a lifetime ago, we use this to separate compounds from mixtures. It can help you determine the progress of a reaction or the purity of a compound. And in this course, we used it for both. So we used it to determine the progress of a reaction in the isomerization lab. Right, so in the isomerization lab, we used it to determine the progress of a reaction. And one more time, I'm just going to drop the link in the chat. If you want to follow along with this document, I have it posted already. Okay. All right. And the purity of a compound, we use that in beta-carotene. Right. So in this course, we did go over both techniques. All right. Make sure you are fully capable to label a TLC plate and identify the different features. Okay. So the tick mark at the bottom, that would be the origin. The solvent front has a line. Majority of the time, like in real life situations, it's not always going to be a straight line. It might be a little curvy, right? But in any case, make sure it's a straight line for the solvent front. Origin's a tick mark, okay? Any spots that you see should be outlined to completion. So if you get a weird spot, something that looks like this, and it's colored in, make that a bit uglier. So if you get something like this, right, on your TLC plate, when you are outlining it, you literally outline it completely, right? So you want to make sure you're outlining these spots, okay? And then down here will just be whatever you're running on the plate. Okay, how fast will a spot move? There are 3 factors that determine how quickly your spot will move across a TLC plate. The following factors are the structure of the compound, the solvent being used, which is also referred to as the mobile phase, and then the stationary phase, which in our course is going to be silica. And so things you want to recognize is that your stationary phase here, right? Your stationary phase does have hydrogen bonding. That means that your stationary phase is polar. Okay, so we do have a polar stationary phase because we do have hydrogen bonding. This is just a nice summary here. This is also on Dr. Hossain's slides. This is just a nice summary of different substances and how polar they are and things like that. Sorry about that, guys. So as I was saying, we have polar compounds and for the stationary phase, and then this guy here is just your interactions and how they're going to work in terms of polarity, okay? So there are 3 criteria every time you're considering TLC, all right? So let's go into a little bit. I know these slides have a lot of text on them. A lot of the text on these slides are from your lectures, or it's me breaking down the lectures, but we're going to kind of go over the main ideas here, okay? So stationary phase, here's the idea. Because you have a silica stationary phase, right? It's super polar. So what ends up happening is if you have silica, right, this guy, when I say stationary phase, you guys know when you're looking at your TLC plates, right? And it has that white stuff on it, the chalky stuff that you're not allowed to touch with your fingers. That's the silica, right? So that's the stationary phase, that white stuff. So what happens is if we have this guy here, okay, and we say put some kind of polar substance on it, okay? I don't know what we're going to put on it. Some kind of molecule that has OH bonds. Okay, whatever. Some kind of molecule. That's the key word here. So there's some kind of molecule with H bonds. What's going to happen is these guys are going to interact, right? Does everybody see that? That this oxygen and this hydrogen can interact with each other. So if these are interacting with each other, this molecule is not going to really move up your TLC plate. It's going to get distracted, okay? However, if you have, say, something that's not polar, right? So maybe you just have a bunch of hydrocarbons, right? Something less polar or non-polar even, and you put it on this silica plate. It's not going to have any care in the world about these OHs. Right? So it's not going to want to react. So it's going to move up the plate a lot faster. Okay. Does that make sense to everybody? If it doesn't, let me see if I could put it in these kinds of terms. Let's use an analogy, shall we? You guys know the Super Bowl, right? Everybody's heard of the Super Bowl. Big football event of the season, happens around February. Okay. If I were to ask you, what do you like about the Super Bowl? I can guarantee you 80% of the population says the halftime show. That's all anybody cares about. You just want to know who's singing. You want to see if there's any big scandal that you could gossip about the next day. Was it good? Did it suck? Right? And then you have that 20% that actually gives a crap about who wins the damn game. Because it's never your state's team. New York sucks. Okay? We never have anyone in the Super Bowl. It's been a really long time for us. Okay? So here's the idea. These guys, these are like my dad. They care about football and the Super Bowl. So they're going to stay until the very end. They get distracted by the game, okay? They're going to hang out at their friend's house, eat, drink, whatever. It's going to take them forever to get home, which means it's going to take them forever to move up the plate, okay? This is normal people, hexanes. These guys are only there for the halftime show. They don't care who wins. Beyonce shuts down the stadium. Hey, it's like 11 o'clock. I'm going home, okay? These guys have no care in the world. They get home faster. Does that make sense? So that's just for molecules, okay? So that's just the molecules. All right, cool. So that's your stationary phase. So that's basically what all of this garbage is saying here. So that and that. Okay, then you have the mobile phase. Now, the mobile phase works completely different than the stationary phase. You can have a polar solvent and a non-polar solvent. So here's the idea, all right? You have a TLC plate, you have your origin, right? You got your little tick mark. We know it's silica. So let's say you put water on this guy, right? What happens is when you have a polar solvent, right? Polar solvent, your spots are going to travel further up the plate. Okay? So something like water, where you have a polar solvent. Let me make this look a little prettier for y'all. Whoa, what just happened? Guys, it's been doing this to me all day. I'm just convinced my iPad's over me. It keeps jumping on me. Anyways, let's say we have a nice TLC plate with water. And then, does anybody know a really non-polar solvent? Anybody remember one that we used this semester? There's a few. Anybody? Yeah, nice. Lidocaine, right? Excellent. Lidocane's atrocious. Okay, super non-polar. So we have polar and we have non-polar. If you have substances that are the same and they're traveling on the plate, in a polar solvent, they're going to travel higher up than in a non-polar solvent. Okay, so you still have that solvent front, you know, all that good stuff, whatever. But the more polar the solvent, the higher up on the plate they'll travel, right? They'll move up higher. The more non-polar the solvent, the less they'll move. Okay, so let's see. So polar solvents, we migrate faster. Non-polar solvents migrate slower. Sound good? Be good there. Cool. All right. Here we go. These were supposed to be questions for you guys to answer, but that's okay. So when we are looking at this, is the stationary phase polar or non-polar? We already answered that, right? In this course, the stationary phase is always polar because it's always silica, okay? Do polar substances interact with the stationary phase? We went over this. If you can hydrogen bond, which means you're polar, then heck yeah, you're interacting with the stationary phase, right? Doesn't matter what it is. If you have hydrogen bonding, you're interacting, okay? So this is just a nice summary slide of everything we kind of just went over. So this means polar substances are too busy. So non-polar substances travel further down the plate. And then in terms of polar substances, right, they won't go as far. Okay, and those are substances, not liquids. Okay, so in this case, red represents polar compounds, blue represents non-polar compounds. So does everybody see how the blue almost immediately starts moving down the plate faster? Does everybody see that? Right, so this is just representing that in a nutshell. Blue will move further down the TLC plate, which means that non-polar substances move down the TLC plate further than a polar substance. Okay, fun times. Let's do it. All right, potential exam questions. And by potential, I just mean they sound good and they were covered in lecture. Would you expect Lidocaine to move spots on a TLC plate? What do you guys got for me? Yes or no? Do we expect Lidocaine to move spots as the mobile phase? So if Lidocaine is the mobile phase, will it move your compounds? Yes or no? Good, it won't. How do we know that? It will not move spots on a TLC plate because it has no polarity. Okay? Does everybody see that? Lidocaine has no polarity, which means very non-polar, so it's not going to move anything if you use it as the solvent. Okay? That's why usually we mix it. We'll do like a 9-to-1 Lidocaine ethyl acetate. You know, we usually mix it with something and we get a good solvent ratio. Okay? Toluene, ethyl acetate, and water. Who is the most polar out of these three? And you look at the polarity indexes, right? The higher the number, the more polar it is. So who's the most polar? Water, right? So if water is the most polar, it's going to be moving these compounds further up the plate to the fact where they may even run off. So water's probably not the best solution to use. What about ethyl acetate? Will that move things? Yeah, right? Ethyl acetate is going to move compounds. Its polarity is about 4.4. It's about in the middle, right? That's a pretty good polarity. So yeah, it's going to move compounds. And toluene has a really low polarity, so it will move them, but just slightly. Okay? Alrighty. So let's go a bit more. Just so you guys know, I do have all the answers typed out for you on the pages after. just so that you have everything I'm saying to avoid copying everything down. Okay. Let's talk about how we can use a TLC plate. The biggest thing you want to gather from this slide is that we use it to determine RF values, right? So RF values are used a lot in this course. What you can do with a TLC plate, like we said before, right? It can be used to determine the rate of a reaction. It could be used to isolate pure compounds and see if you have them. The other thing you want to remember here that was on your lecture slides is if you only get one spot, it could represent a mixture. So if you only get one spot on your TLC plate, it could potentially represent a mixture of compounds. Okay? All right. RF value, make sure you know this formula. So RF, distance traveled by the compound divided by distance traveled by the solvent. And when we're doing this, you're going to use the middle of that dot there. Okay, so make sure you know how to calculate RF. So distance of the compound over distance traveled by the solvent, which is from origin to solvent front. Okay. What do you guys remember about RF values? RF values 100% reliable. Crystal's here, guys. OMG. We have a famous visitor. Beautiful. RF values are not completely reliable, right? And the reason why is a lot of compounds can have the same exact RF value. Okay, so they're not completely reliable, but they are useful in a sense that if you're comparing the RF of your compound to a standard, like we did in beta-carotene, right? We had a standard beta-carotene and the one that we purified, and we ran that TLC plate. Comparing those RF values is okay because the conditions are the same and you are comparing the standard. Okay, all right, awesome. So taking a look at this guy now. This is just talking a little bit about polarity and movement. So the first thing I want to ask you is between blue and black here, who do you think is compound A? If compound A is a polar compound, who is compound A? Do you remember what we said about these guys? Okay, let's review it a bit. Remember that non-polar substances travel further up the plate, right? So yeah, excellent. The black spot, this is going to be compound A. Okay, once again, compound A is the black spot because it is more polar, which means it cannot travel as far up the TLC plate as a non-polar compound, okay? What happened here to compound B? So in this very last one, right, compound B was more non-polar. However, the mobile phase or the solvent being used was very polar. So what this means is that it ran off the plate completely. So the TLC ran too long. The solvent was too polar. Okay. Is this stuff making sense to you guys? Hopefully it is. I don't know. Those of you watching at home, I hope you're enjoying yourselves at a later time. So here we go. Next slide, isomerization. So that was just kind of a TLC recap. Now we're going to get a bit into the reactions. So the first lab that this theory quiz covers is isomerization of dimethyl malleate to dimethyl fumarate. What do we do here? We use TLC to monitor the reaction. Okay, so this is where you had standard, and then you had like 0 to 10, 20 crystallized, right? And you had to do different spots at different intervals. It turned orange. Some of yours became clear, right? So this is that reaction just to kind of get you familiar with it. So what happens with isomerization is our goal was to create dimethyl fumarate. We used Br2 over light, right? You had to use heavy duty gloves. If you're interested in the mechanism, here it is. So this is just the radical reaction. Here is just a rotation step. And when you're looking at these different kinds, this reaction is completely reversible. But the idea is that the trans double bond is much more stable than the cis double bond. And that is because there's less steric hindrance here. So due to that increased factor of stability, more of these are going to form over time as the reaction progresses. Okay. This reaction did take longer than 20 minutes to go to completion. It's just that for you guys, we only have so much time in a lab. So we just had you spot it for 20 minutes. Okay. All right. Other useful crap, just things that I've been asked. So if you have tailing, that means you overspotted. So tailing is when you have a beautiful little plate, right? Origin, solvent front. Make sure you can label these things. And tailings, like when your spot looks like that, it looks like a little worm, right? So when you have like a little wormy spot with some tailing, that just means you might have spotted too many times. I know some of you asked me in my office hours about that the other day. I would say the very key idea, actually, I'm not going to tell you the key idea because here you go. 3 questions for you. Look at these. Aren't these pretty? All 3 of these questions came from your lectures. And this one was supposed to have a picture. So, oops. I'm dying. Okay. I was just going to talk to myself. Thanks, guys. So number 3 is supposed to have a picture. I'll add it in later. Hopefully I'll remember. But does anybody know why we added ice cold hexane before we performed vacuum filtration? Let's start with that one. That's a fun question. So when you were performing this lab, right, you guys got to make sure you're familiar with these procedures going into Monday, but you still have a whole weekend. So it's great. So yes. So in cold hexane, excellent, Hannah, both dimethyl malleate and dimethyl fumarate are insoluble, right? So I'm going to abbreviate them as dimethyl malleate, dimethyl fumarate. Both of these guys are insoluble in hexane, okay? However, if you look at their melting points, there is a huge difference. One has a melting point of like -19, which I believe is dimethyl malleate, and the other one has a melting point of like 100 something, okay? So what happens is they're both insoluble in cold hexanes, the difference being that dimethyl malleate comes out in a liquid form, okay? This was emphasized on your lecture. So dimethyl malleate will precipitate out of solution in a liquid form. So when you're performing vacuum filtration, only the dimethyl fumarate will be crystallized. Does that make sense? Okay. And like I said, I do have a key with all of the explanations I'm saying out loud written out. So I'll have all the explanations posted for you guys at the end as well. Okay. Next question. Dimethyl malleate versus dimethyl fumarate. Let's take a look at these guys again. Here they are. So dimethyl malleate versus dimethyl fumarate. Who would you expect to be more polar? I like this question. I think it's fun. Also from lecture. Like I said, guys, I spent the past 2 days watching your lectures. Just having a blast. Excellent. Yeah. So dimethyl malleate is in fact more polar than dimethyl fumarate. Very nice. So to answer this question, it is false. Excellent job, everyone. Very, very nice. Okay, cool. So why then? Why is this a thing? Here's what happens. Dimethyl malleate is more polar because of this asymmetry, because these groups are on the same side of that double bond, it creates what's called a dipole, which you don't have to worry about too much. But just understand that because this is symmetrical, the like forces cancel each other out. So this will not have a net dipole. This will, which causes it to be more polar. Okay. All right. So then one more question for you, since I forgot the picture because I'm special. Sorry guys, I was making these slides today, and I also had my nieces, who are a year and a half. And then it turns out that for Good Friday, everyone's off from school. So I had my nieces, my 2 nephews, and then my cousin slept over last night. So I had 4 kids under the age of 5 and then a 10-year-old today. It was a joy. Okay. And this was from 7 a.m. to like 5 p.m. So it's been a blast, to say the least. Just, you know, if you ever need reassurance as to why I'm too young for kids, it's this. I really am a mom. It's so bad. Okay. So let's say, I don't know, we got a spot here. Hey, Crystal.
Hi, Gabby.
And a spot here.
Order queen.
Never.
At it again.
Oh my God. This is all I do with my life. You didn't know? I had a review last night, review tonight, one tomorrow afternoon. It's great. It's a party.
Wow. Nonstop. You're on a roll. Gosh. I can never.
Oh my God, I'm dying. All right, guys. Dimethyl malleate, black or blue? What do you got for me? If it's more polar, good, it's blue. All right, some of you guys understand PLCs. That's good. Don't worry. By Monday, you'll all be professionals. So this is dimethyl malleate, and then this is dimethyl fumarate. And we know that because the more polar compounds are closer to the origin line, more nonpolar compounds are closer to the solvent front. Excellent. Next. Here you go. I doubt you guys will see something like this because this is ridiculous, but I thought it was a fun question. You know, we can't discredit the fun. So go ahead and try this out. I think I have polling. Yeah, I do. Cool. Okay. So if you're brave enough to read this like it's an English class, go ahead and try this question out. Hold on, guys. I'm going to turn my light. There we go. It was like really bright, like a half hour ago. Oh my goodness. Somebody got it correct. If you answered and your answer wasn't help, you did a good job. Oh, you guys are listening. Oh, this makes me so happy. I'm not gonna lie. Like I said before, I'm shocked this many people showed up on a Friday. It's really kind of you all. It's much appreciated. Do. All right, a few more seconds, then we're going to go over it. Alrighty, let's do this. So everyone who answered it crushed it entirely. So the correct answer here is, in fact, D. Very nice. So here we are told towards the end of the isomerization experiment, you collected crystals by vacuum filtration. TLC results of that solid product suggested that the product collected was dimethyl fumarate. However, TLC results also indicated both dimethyl malleate and fumarate were present in the reaction mixture after 20 minutes. So what happened to dimethyl malleate? We just talked about this, right? its melting point is so low. Oh, look, I got that right, -19. So because the melting point is so low, when it precipitates out of solution, it's actually in its liquid form, okay? So it does precipitate out, but instead of being a precipitate per se in a crystal, it is going to come out as a liquid form. Very nice, everybody. All right, I got one more of these, and then we're gonna head on over to the next lab. So try both of these out. One thing I will say is that when studying for your theory quiz, definitely prioritize Dr. Hossain's lectures as well as your lab reports over previous theory quizzes. Because since this is his first semester as like a full lecturer, he has a lot more input in the exams, meaning he literally makes them. So they're going to be more based off of his lectures. Whereas in the past, you know, theory quizzes are made by other professors. So definitely focus on your lab reports and your lectures. Okay, those will definitely get you through for this theory quiz and they'll help you do really well. Alrighty, guys. So here we have Emmanuel. He is running a reaction for the first time. So he decides to monitor it. This looks just like the isomerization lab. So let's take a look. When we're looking at this, we see that he spots every X minutes. We're given it at time 0 and we're given the final. So time 0. Is this before the reaction starts or has the reaction already started? Yeah, so time 0 is before the reaction has occurred. So that means at time 0, this is pure reactant A. Right, so that means A is the starting material. Does that make sense? So the reactant is represented by A because this is the only compound present before this reaction begins, okay? What about at the very end, right? You see how the reaction is driven to completion here. And we know that because there's only one spot. Now this spot has traveled far enough for us to know that it's most likely not a mixture. So this means that this guy is going to be our product. So our product is represented by spot B. Does this make sense to everybody? We're good. All right, let's hear me talk some more. Beta-Carotene, here we go. Here's a bunch of images. Isn't this pretty? You guys know exactly what all this means, right? Like I don't have to sit here and be like, here are some pretty pictures. You should know what they do and what they look like. So stationary phase, right? That's your silica, okay? Beta-Carotene, we're using the same stationary phase. Then we have beta-carotene, chlorophyll A, and chlorophyll B, okay? If you're relating this to your column, chlorophyll A and chlorophyll B are that green crap on top. Beta-carotene was the yellow stuff towards the bottom, okay? So then let me ask you a question real quick here. Who is more nonpolar, chlorophyll A, chlorophyll B, or beta-carotene? Feel free to type B for beta-carotene, CA for chlorophyll A, and CB for chlorophyll B. That's a lot of words. Oh my goodness, my voice, my little voice box. I've been yelling at kids all day. B, excellent. B for BB. Love it. Okay, so yeah, beta-carotene, right, is more nonpolar. Guys, this is all hydrocarbons. There's literally no oxygens, there's no hydrogens, there's nothing fancy like a magnesium, okay, like these guys have. So beta-carotene is the most nonpolar, right? So now let's relate this to TLC a little bit. If we were to toss this sucker on a TLC plate with chlorophyll A and chlorophyll B, is it going to be the highest one or the lowest one? If it's the most nonpolar. Beautiful, it's the highest. Very nice, very nice. right? It's going to be the highest one because it's the most nonpolar. So it's going to travel up the plate the fastest. It's not going to get distracted by the silica. Very good. This is me at the Super Bowl. Very nice. Very nice. All right. Column chromatography. So for this lab, we did a lot of TLC, but we also really focused on the columns. The cool part about columns is that if you understand TLC, you understand columns. Columns is just a TLC plate turned upside down. So we use this to separate columns, to separate compounds on a much larger scale, okay? Let's go ahead and let's take a look at just some info on column chromatography, okay? So for column chromatography, like the TLC plates, it does have a stationary phase and it does have a mobile phase. So I have this little chart which summarizes them a bit for you. So for the mobile phase, your mobile phase in a TLC plate, you travel bottom to top. In a column, you travel top to bottom, okay? For nonpolar compounds or nonpolar solutes, things like that, they're going to be closest to the solvent front in the TLC plate, which means it's one of the very first bands to come off the column in a column chromatography. All right, you guys can read the rest of that. It's fun stuff. So column chromatography and how it relates to TLC. We just did all of this. I'm thinking, is there anything else important? Yes, there is. This sucker. Where's he at? The location. Location. This has a lot to do with the solvent you choose. So a lot of times what people will do is they'll use TLCs to determine what solvent ratio to use for a column. And what you want is your ideal separation on a TLC plate should be a spot that's like near here, and then one that's greater than 0.5. If you have both spots greater than 0.5, they're going to come off the column so quickly that you're not going to be able to separate them. Okay, these bands are going to overlap. So if you have a good distance where one is below 0.5 and one is above 0.5, sorry, I'm laughing, guys. Just look at Crystal's video. It's making me die right now. If you have one below 0.5 and one above 0.5, that's going to give you really good column separation. Okay. All right. More factors that influence. Are you guys done with columns? I'm so done with TLC. I don't like TLC at all. Full disclosure. I think it sucks, but here we are. So stationary phase, same exact idea, right? We're using silica once again. Nothing there is changing. So we're using silica for our stationary phase. So same idea, right? Polar compounds are going to get stuck at the top. Non-polar compounds are going to come out first. Okay. So when we say it's going to elute faster from the column, it just means that sucker is going to come out faster. Okay. As far as mobile phase is concerned, polar solvents will have compounds go faster than non-polar solvents. In your lecture slides, Dr. Hossein represents this really, really well with TLC slides. He gives you all like 3 or 4 different slides. I think it's 2 different slides where he has different scenarios of which solvent is better, and he actually shows you the TLC plates and the results. Looking those over would be phenomenal. At the end, I'll show you exactly what I'm talking about because I have all his slides on my iPad. But it's so, so great, the slide that he has, because it shows you the breakdown of how everything separates at different solvents. So normally for this lab, we would use like 100% Lidocaine. And as you know, Lidocaine is really nonpolar. So it takes a really long time for those bands to come off the column. But this semester, we gave you a 9-to-1 ratio. So we made the solvent a bit more polar. And that made the columns elute a lot faster. So knowing the different polarities is going to be really helpful here for you. All right, let's do it. Next, factors that influence it. Just a few ideas here. If you have a lot of silica, that's the idea that you want to go for. You know, you want to have enough that's proportionate here. This is just an example of what your column might have looked like when you ran it, right? So you have your green bands here. This was chlorophyll A and B. And then this was your beta-carotene. So like you all predicted, it's more nonpolar, so it's going to travel highest in terms of the TLC plate, and it will come off the column first. okay? And a lot of you guys did great on this. In terms of math, you want to be able to determine column volumes. So a column volume is just 1 over the RF value. Just have a general understanding of what it means. It's the mobile phase contained within the stationary phase. And yeah, I mean, the amount of column volumes, it really does depend on how well it's absorbing. But just the general idea of it, as well as column volume, is 1 over RF. You know, you guys got this, okay? Monday's going to be a piece of cake for you. So potential test questions. I think I just gave you the answers to these, but think on them for a minute anyways. So you guys know how Easter's on Sunday? My family like celebrates Easter. Like, you know, we have people over for lunch or dinner, really. We do like a dinner, an early dinner. Like my grandparents come over, but my siblings and I, like the youngest is 18. So we really celebrate it for the kids. But I will say my dad just came in my room and I got peeps. Can you see them? There they are. Little peeps, which is what you guys are, your peeps. And then I got Robin eggs. I don't know where I'm going to be on Monday, but do you guys want me to bring in like candy for after your theory quiz? So it's like hand in your theory quiz, take a piece of chocolate, you know, because the day after Easter, it's all going to be on sale anyway. So it'll be like 75% off. So you guys will get Easter candy a day late. I'll bring you guys candy in. I'll give you something to look forward to after you take your quiz. All right, here we go. Beta-carotene, is it coming off the column first or last? What do you got for me? We answered this like 20 times already. It's coming off the column first, right? Why? Because it's the most nonpolar out of the compounds that we're using. Why do we run the column with 90% Lidocaine? I actually just touched on this a bit. So we use 90% Lidocaine as opposed to 100% Lidocaine because it will be faster. And if you look at Dr. Hossain's slides, he also indicates that it gives you a better separation. Okay. Like I said, guys, I watched all your lectures the past 2 days. So I crash coursed your course just to make sure that I knew what I was talking about. So awesome. So we run it with 90% Lidocaine because it's going to be faster. And the separation is going to be much better so that we can really get pure beta-carotene. Very nice. Here's a question. Let me pull it. So far, is this helping you guys out? Is it making sense? Like, is it jogging your memories on these labs a bit? Yeah? Okay, cool. I'm so happy. Good. That makes me happy. All right, cool, cool, cool. Oh, anytime. I have nothing else to do on a Friday night. The only thing I have planned for tonight is recording Orgo videos. So procrastinate 322 with some 327. That's the kind of life I'm living for. I don't know about you guys, but that's my Friday night. I'm waiting for good movies to come out. I just bought tickets to Doctor Strange because they're almost sold out already, which is ridiculous. It releases in like a month. So I got to wait a whole month to see that. But yeah, chilling. Oh my God, I should. Yeah, HNMR will not be on the exam or the quiz. Yeah, we cut it out. We were not about it. Instead, he gave you a whole lecture of review, which was really kind. Because no theory quiz, no Orgo lab professors ever do that. Also, if you guys didn't check out those review slides, make sure you do. There's a ton of math problems, which are your favorite. So definitely do those, guys. All right, let's go ahead and let's go over this. There seems to be just a small bit of confusion here. So these three TLC plates were developed with different solvent systems, but they have the same two compounds mixed within them, okay? We want the order that will have them going from worst to best separation using column chromatography. So just about all of you got it, right? One is the best. Hands down, no doubt about it. If we were to divide this TLC plate in half, right, it would look something like that. So the fact that one spot is below half of the plate and one spot is above it, one will most definitely give us the best separation. Okay. Then when we're comparing 2 to 3, right, this requires a little bit more thinking because in 2, they're both below halfway, and in 3, they're both like right above halfway. So now it's a matter of which one, even though they're both not going to be the best, which one is the better of the two. So in this case, 3 is the worst. And the reason we say that is because remember, you do not want both compounds to have an RF greater than 0.5. These are going to come off the column so quickly because they're both super nonpolar that it's going to take not going to take forever. What am I saying? They're going to come off the column so quickly that you're not going to be able to separate them. You're going to get very poor separation. So the correct answer here was F. 3 is the worst, then 2. 1 is the best separation. Okay. Alrighty. I got one more of these guys, and then we're going to go ahead and we're going to start talking about esters a little bit. So remember, like I said earlier, this is most certainly not a full encompassing review. I can't guarantee I'm covering everything, but like, you know, it's better than sitting there and being like, oh my God, I have a theory quiz on Monday, and then Sunday at midnight starting to study. Okay. Like if you're watching this back and it's not Sunday at midnight, where you're watching this live right now, like you're putting in the work now. So it'll save you a little bit of time later, you know? If you are watching this on Sunday at midnight, get some sleep, get some coffee. I don't know what else to say. I'll have candy for you on Monday. I don't know if that makes you feel better. Okay, so if you read the English paper, that is the question here, you'll see that we're trying to isolate the lowest spot on the TLC plate. Okay, so when you're looking at this, we're trying to isolate the lowest spot. Good. All right, let's go over it. So we're isolating the lowest spot. So that means that in this case, we're isolating the most polar compound, right? None of that matters, but good review here. We're isolating the most polar compound, which means because it's a polar compound, it's going to take longer to come off the column, right? Which is fine. We got all the time in the world here. Most of you agreed A and D were the worst, and I agree wholeheartedly, right? In D, all 3 of them are almost above 0.5, which we said in the last question is awful. So how do we distinguish between B and C? Well, if you take a look at C here, right? You see the separation. These guys are both above 0.5. Normally, that's not ideal. However, in this case, it's great because we want to isolate this guy, right? So because we want to isolate this substance, the fact that the 2 of these will run off the column pretty quickly together tells us like, hey, these guys will go, and then we can definitely get just our guy by himself. Okay, so the best separation here is going to be C. And most of you got that correct, so really great job. All right, on to esters. Naming esters is crucial. make sure you know how to name them. How to name an ester, you take the alcohol component, mash it with the carboxylic acid component, okay? These are just a bunch of examples. The best way to go about this is the following. Let's say on the exam, you're given an ester. The way you want to break up an ester is you're going to slice it right here, okay? This guy on the left becomes your alcohol piece here. This guy on the right becomes your carboxylic acid piece. So you have your alcohol and your carboxylic acid. Oops. So this has an ethyl group and it's OH. So ethyl with an OH is ethanol. And then this guy also has 2 carbons. So this is eth again. And it's going to be ethanoic acid, or it could also be referred to as acetic acid. Okay. So the parent alcohol is the first name of an ester, and then the parent acid, that's the second part of the name. Everybody good there? So if you're given the names, which you should be given these names, you know, you'll get like this guy plus this guy equals what, and then name me, or they'll give you, here you go, and they'd be like, what components is this guy made of? So then you take the propyl, it becomes propanol, and then propanoate just becomes propanoic. Okay. Does that make sense to everybody? So you'll either be given, you know, methanol and benzoic acid and being asked to name what the product is, or you'll be given the ester and being asked to name its components. You know, what makes it up. Okay. Awesome. So let's get a little bit into the reaction now. So this is a reversible reaction. If something is reversible, you know, it happens kind of slow. So we do a lot of things to fix this. We add catalysts, we add heat. The catalyst we used in this reaction was concentrated H2SO4, right, sulfuric acid. Or you can add heat, which we also did. We used a reflux in this case, and that can also speed up the reaction a bit. Another thing you want to do is if you want to increase the yield, you can add excess reagent. So you could use a lot of carboxylic acid. You can remove a product. Just some info. These guys are just straight from your lecture slides. Here's the mechanism. Fun fact, if you're taking Orgo 2 right now, this was actually on the exam you just took, this exact same mechanism. So you already know it, hopefully. And if you don't know it, you know, just review it a little bit. Just have an idea of what's going on. Okay. Here we go, the fun stuff. So in the ester lab, you were able, or you were given the privilege of running your first set of separations, right? You used your separatory funnel. Please, please make sure if you review anything from Dr. Hossain's lectures that you go back to this slide. Okay, make sure you listen to him explain this process over and over again. It's crucial that you understand what's going on here when you're doing these washes, when you're doing these reactions. Okay, this is like the holy grail of what this lab is about. Like if you could summarize it in one page, if you can explain this to me front and back, like you understand the ester lab, no problem. Okay, so 5 reagents, you have your alcohol, you have your carboxylic acid, you have your H2SO4, which is your sulfuric acid, you have your ester, you have your water, and that little triangle represents heat. So we got all of our components, okay? So the first thing you did was you added the diethyl ether and water. What happens here, right? What dissolves things like that? You end up having 2 and 4. So your carboxylic acid, right? That will mix with your alcohol. When carboxylic acid and alcohol mix with a little bit of acid, you get your ester, right? 4 is the goal here. We want to separate 4 from everything else. So the idea here is that we should definitely have 4, right? That should definitely be one of our products. If you remember in this lab, the alcohol, this was our limiting reagent. So ideally, number 1 should be gone because we added so much acid that there shouldn't be any alcohol left. However, there could be some left, right? It's not completely out of the loop. Theoretically, it should be completely gone. But practically, you know, we're human. We make mistakes. Maybe all of it didn't react. So there could be a little bit left. All right. And then in your water, you're going to have 5, 3, and then 1 and 2. Okay, so anything that really didn't react. So next, what we do is we did that. We washed it with water. Yay. Then we washed it with sodium carbonate to remove any extra carboxylic acid. So your carboxylic acid, once again, that's structure 2. Okay, so when you washed with your sodium carbonate, you're removing any carboxylic acid that's left over. Okay, sodium carbonate is a base. Base removes acid. Makes sense. Okay, then you're going to have hopefully most of your ester at this point. Okay, if you don't have most of your ester, the other option would be some carboxylate. And then in this case, you're just going to dry it with the magnesium sulfate, and that's going to remove your water. Okay, so just make sure you guys review this slide. It's super duper important. All right, so the main idea in terms of theory here is going to be IR. Yes, the ester is number 4. So that's your ester. This is your carboxylic acid. And then this is your alcohol. Okay. All righty. So IR, these guys, there are certain peaks you should be able to recognize in this course. And they're all listed here kindly for you. So you should be able to recognize OH stretching. Okay, so it usually occurs at about 3,600. If you have just an alcohol, like this guy, right? You have some kind of alcohol here. You ready to see my beautiful drawings, guys? At about 3,600, it should look like a U. Should be like a nice wide shape with some, some other stuff, whatever. Okay, but ultimately at about 3,600, you should see a long U shape, and that indicates an alcohol. Okay. Does everybody see how this guy looks like a U shape, but it's like deformed? It almost looks like a cow udder, or like if you're going to milk a cow, that's what I refer to it as, a cow udder. Anytime you have this cow udder looking thing, this is a combination of that alcohol stretch with that carbon hydrogen stretching. Okay, so anytime you see fancy cow udder and you see a really long, narrow peak between, I think it's like 15 to 1700. Let me just make sure. All right, they're giving it about 1700. So about 1700. That will tell you that you're double bonded up. Okay, and this is in fact the IR of this compound here, of this carboxylic acid. So you have your OH stretching mixed with your carbon hydrogen stretching, and then a really narrow peak. So make sure you can do IR spectrum. Definitely, I'm sure, like 87% sure there's going to be one of these on the theory quiz, just because there usually is one. So just make sure you can identify these stretches. Okay. I also have a YouTube video where I go really in depth on this. So if you're interested in learning more about IR and how to recognize these stretches, I'll put the link for that video in the folder where the recording will be, as well as the document that we're working off of, okay? All right. So let's do this. The student takes an IR spectrum of the benzoic acid he isolated in the first step. What is the expected IR spectrum of benzoic acid? So what I'm going to do for you is label these A, B, C, and I'm going to go ahead and pull it. So which one of these guys is carboxylic acid? A, B, or C? right, guys, let's go ahead and let's start going over this. So if we all agree on one thing, it's that it's definitely not C, right? C doesn't even have that peak at about 1700 to tell us it's a carbonyl, right? 1700 is about here. So if there were at least a double bonded O, there would be a nice strong peak here. Let's go ahead and let's start recognizing these a bit. So this guy right here, that's a double bonded O, right? We have a strong, pretty narrow peak at about 1700-ish, okay, between 17 and 1800. The other thing we have is at around 3000, we have the stretching. Now, I think a lot of you got confused with this. So because this is at 3000, this is actually just going to be carbon-hydrogen stretching. Okay? When you're looking at structure B here, we once again have that long, strong, narrow peak. That's your double bonded O. Now, at 3000, right, we have our carbon H stretching, but we also have this piece. So this is another way that you could illustrate a carboxylic acid. Okay, so this guy is indicating a carboxylic acid. So B is the correct answer here. Does that make sense? So if you're going to compare A and B, right, A just has that carbon stretching, whereas B does have this little peak here where it's really broad, right, really wide. Okay, and it's coupled with carbon-hydrogen stretching. Okay, let's try another one. So here, I know the writing's pretty small, but ultimately what they're saying is that reactant X is a ketone. So it's methyl isobutyl ketone. So X is essentially just a double bonded O. And Y is 4-methyl-2-pentanol. So Y is just the alcohol. So what we want you to do is see if you can label these guys appropriately, figure out which one is X and which one is Y. Okay. And once again, X is just the double bonded O and Y is just the OH. So take a minute or two on your own and see if you can come up with the answer here. All right, you guys are doing great. Really, really great work tonight. All right, let's go ahead and let's get over it. Go over it. So let's identify some functional groups. So in the first structure here, I have my carbonyl peak. I have carbon-hydrogen stretching. In the next one, I do not see a carbonyl peak, right? That's absent. I see some carbon-hydrogen stretching, and then I have an alcohol peak. Does everybody see the difference between the alcohol and what a carboxylic acid looked like on the previous page, right? You see how they're kind of joined, right? The OH and the CH stretching, whereas in the next one, they're completely separate entities. Okay, and then in the very last one here, we have a double bonded O stretching, we have an OH stretching, and a carbon-hydrogen stretching. So that means this first one here should be X, and this should be Y. If I had to draw a structure for this guy, it would most likely be, not exactly, but maybe something like that, where you have the double bonded O and the OH, but it's not a carboxylic acid. And the reason this one wouldn't be a carboxylic acid is because the OH and the CH stretching are not like conformed together. Okay. Alrighty, let's try another. Which of the following compounds is this guy? Let me pull it. There we go. So the last one, we just had to identify X and Y. So X was the first one where you just had the carbonyl, and then Y was the second one where we just had the alcohol. So it just told us what the structures were, and we just had to match up the structures with their respective IRs. Yeah, anytime. You guys are crushing this one. So I see you're finally getting the hang of IR, which is great. Super awesome. Okay, just a refresher if you're confused. Propanoic acid is a carboxylic acid. Two-methylpropanol, the fact that there's OL at the end, that tells you it's an alcohol. And then ester, I mean, that's self-explanatory. That's an ester. Okay, good. That helped a couple of you. Okay. All right, let's go over it. So everyone got it correct, 2 answered. So really great job, guys. Very nice. The answer is in fact B, 2-methylpropanol. All right, we have one more topic to cover for ester, and then I think I have like 4 or 5 questions that kind of gives you a summation of the whole lab. Gas chromatography, this is what you did when you went in the instrument room. So you did the IR spectrum, you got your results, and then you got your GC results. When you're looking at gas chromatography, there are some few things that matter the most. I know there's a lot of writing here. I just crammed it all into one slide for the hell of it. Key things: compounds coming off the column earlier have lower boiling points. So when you're looking at a GC, all the way to the left means it's coming off first. Those are going to have lower boiling points. Okay, that's really all that matters. I mean, this is important as well. The size of the peak, the larger the peak, the more of that sample you have. Okay, so when you guys got your ester GCs, a lot of you should have seen like maybe a little blip for air. And then you should have seen like a really big one for your ester. And that should have been it. If you had 2 esters, you might have had a second part that went a little like that, right? So if you had 2 esters, you might have had 2 lines. Okay. So this is what your GC might have looked like. So here we could see that we have some air there. This is response. This is retention time. The response is what determines your purity. So here, this student had 95-ish% purity, and this was their ester. Okay, this is what a GC looks like. In terms of boiling point, this one would have a higher boiling point, whereas this would have a lower boiling point. Okay, so just some fun things there. to look at. So as time increases, right, we could see that the boiling point is increasing as well. Okay, let's do some questions. Here we go. Try these out. There's some math involved. So I'm going to let you guys read these. I'll be back in just a minute. Okay, so just read through this and then we'll run through it together, but I'll be right back. Just give me a minute here. Alrighty, let's do this thing. So for this question, there's a lot to take in. So it says that this is a Fischer esterification reaction. Essentially, in a round bottom flask, we have 10 mLs of propanoic acid, 10 mLs of 2-methylpropanol, 2 mLs of sulfuric acid. Okay, we heat it under reflux, dissolve it, sodium carbonate wash, dry it with anhydrous magnesium sulfate, roto-evap, and then we distill it. They want to know who the limiting reactant is. Based on the information given just in this blurb, we cannot determine who the limiting reactant is. What we have to do is calculate how many moles of this stuff we're given. Does that make sense? So when you performed your lab, right, you were told, okay, 0.05 moles of alcohol and 0.1 moles of carboxylic acid, and then you were told to find the grams, right? Find the mass of that, and then you weighed it, right? All that good stuff. So for this question, we have to take the information given, and we have to figure out how many moles this is. And only then can we determine the limiting reactant. So let's start with propanoic acid. Can everyone see the blue color okay on the screen? Okay. So with propanoic acid, we are told that we have 10 mLs. Our ultimate goal is to turn milliliters into moles, right? So we have to use this information here. So we have 10 mLs of propanoic acid. The only option we have is the density, right? Density will convert mLs to grams, and then we can use the mass to turn grams to moles. So we have 10 mLs. Our density is 0.99 grams over 1 ml. And then we use the mass, and the mass is 74 grams per 1 mole. We do some mathy math. I don't have a calculator. I'll use my phone. 10 times 0.99 divided by 74. We have 0.134 moles. Does that make sense to everybody how I went about this? All right, because they have different densities, they have different weights. Oh, actually their weights are the same, but they have different densities. So the amount of moles is going to change a bit. All right, now let's do 2-methylpropanol. So 2-methylpropanol, we also have 10 mLs of that. Then the density is 0.80 grams per 1 ml. And then we multiply by the mass, which is 74 grams per 1 mole. And then we math it, and we get 10 times 0.8 over 74. And that equals 0.108 moles. So based on this, who is the limiting reagent? A, B, or C? Good. The limiting reagent is 2-methylpropanol. That's a big highlighter. So 2-methylpropanol, that's my limiting reagent because it has the lowest amount of moles, okay? Now they want the theoretical yield for this reaction. Anybody? Okay. Does anybody get confused with theoretical yield? Like you see it in lecture, right? And it makes the utmost sense in the entire world. And then you attempt to do it yourself and you're like, so you just pull these numbers out of thin air? Like it doesn't even make sense half the time, right? So let's try to make it make some sense here. So we need the theoretical yield of this reaction. For the ester reaction specifically, our limiting reagent was the alcohol. And in this case, it's the same exact idea, right? 2-methylpropanol. No matter what we do, right? No matter how perfect of a lab student you are, what is the most amount of 2-methylpropyl propanoate that we can get? The highest amount we can get is 0.108 moles. Does that make sense? Because once we run out of this guy, the reaction's over, right? We can't do anything else, okay? You guys ever play a fun game with your gas tanks, especially with prices right now, where I'll have like a little less than a quarter, and I'll sit there and I'll be like, I can make it 20 minutes away. Like I can make it to campus, no problem. Even if I hit a little traffic, right? I can make it there. You guys ever play that game? Well, if your ass breaks down, right? You're only going that certain distance. No matter how hard you try, you will not go any further. Once you run out of gas, it's gone. Okay? You're not going to be able to go any further. Your car's not going to be able to move. You're just stuck. Think about that when you think about limiting reagents, right? The most amount of this product we can get is 0.108 moles. If my tank only has 5 miles left in it, I'm only driving 5 miles, right? I can get out and push while it's in neutral, but we're going to pretend that doesn't exist right now, okay? So that's it. That's all we can create. So the most amount of product we can get is 0.108 moles. So what we are going to do is we are going to take that value. I'm going to put TY for theoretical yield. We have 0.108 moles. They want it in grams. Grams of what? Do we want to know how many grams of methylpropanol we're going to create with this? No. Do we want to know how many grams of propanoic acid we're going to create with this? No. We want to know how much of our ester we're going to make with this. So we are then going to put here 130 grams over 1 mole. Moles cancel out. You're left with grams. So we do 0.108 times 130, we get 14.1 grams. So that is the theoretical yield. That is this. If everything goes as planned in this reaction, that's how high we can get. Okay. Does that make sense? Okay. Let's do it. Next one. So this is just the same question. And then our next question here is, after reflux, the cooled reaction mixture was dissolved in diethyl ether. The total volume of the ether solution was 100 mLs. The solution is transferred to a SEP funnel. What size SEP funnel is the best? I'm going to go ahead and pull this. All right, guys. So looking at this, excuse me. Here we go. Everyone who answered got it correct, which is awesome. So we have 100 mLs of solution. Think about your separatory funnel that you had in lab, right? If you have 100 milliliters of solution, do you want to use 100 ml sep funnel? No, right? The liquid's going to potentially, like, it's literally going to be overflowing. That's ridiculous. So definitely not that. Definitely nothing less than 100. What about 125? Do you think that will give you enough room to do your shaky, separate your layers? No, right? You need more space. So we need to use the 250 ml. The 250 ml is a great size. There's a buffer of 150 mLs, right? So we could do a shaky shake. We could let the layers separate nicely. It could take its time. Okay, we're not going to worry about it overflowing, nothing like that. 500 is a bit ridiculous. That's pretty big. So the correct answer here is choice D. Okay. All righty. Let's go ahead and let's do this guy. And I believe this is our last question, and then we're on lidocaine. So we're almost done, guys, and you're doing phenomenal. Really, really great job. So try this one out. I'll go ahead and pull this as well. This is just a fun question on GC. Really quick, if you're struggling, remember for gas chromatography, we care about boiling points. Okay, that's really what we're looking at here is boiling points. Okay, let's start going over this because the answers are a little all over the place. So let's first just look at the structures, okay? Like I said, we want to focus on boiling point. So for gas chromatography, right, for GC, if time is increasing, you're going to have your lowest BP here, highest here. So if I label these 1, 2, and 3, okay, or I'll use A, B, C. So if I label these A, B, and C, let's arrange them in order of increasing boiling point. So the lowest boiling point is B. Then C, then A. Now this is the product after distillation. That's the key term. This is the product after distillation. When you reach the distillation step, who should be pretty much gone? A, B, or C? Yeah, excellent. So this is where this question gets a bit complicated, right? You have to remember that flow chart we went over. So after distillation, there isn't any B left. So there's no way B is on this GC, right? The only thing that should be on the GC, technically speaking, is the ester. If you made an error, you could potentially have some propanoic acid left, right? But you really should just have the ester at this point. So now, does this make more sense? So this is our ester. This is propanoic acid. Okay, so that means propanoic acid has a higher peak. So it's the most. So the most we have is propanoic acid. Then we do not have any alcohol left. And then the ester is the least amount.
Gabby, I have a question.
Yeah.
So for the propanoic acid peak, you see that little bump to the side of it?
Yeah.
What is that?
That, it could be a few things. I mean, it could just be just the way it kind of came off. It might not be perfect. With these guys, a lot of the time, they're not perfect peaks. Like if we take a look here, I mean, these actually look pretty good, don't they? Damn. It's a crappy drawing. That's what I'm going to sum it up to. But yeah, I mean, occasionally they might not be perfect. This could be a little air spitting off. Usually the air peaks over here, but it could have been over there. You know, there could have been some contamination in the GC machine. There's a few things it could have been. That's a really good question. Yeah, of course. Alrighty, everyone. Let's keep going. So everyone's good. So we have ester is present in the least amount. Propanoic acid is the most. And the reason for that is because we're at distillation and there's no more alcohol left at this point. All right, last lab, let's do some lidocaine. So for lidocaine, multi-step synthesis, right? This lab took forever. We're still not done with it because next week when you come in, you're going to take the melting point, or I guess that's this week, whatever. Anyways, it's a long process, okay? So let's just talk about the reaction. These are the reaction arrows in case you want them. So this would come in attack, kick up. You'd have to draw out an intermediate and then it would come back down and kick out. I wouldn't worry too much about these arrows. Just have an idea of who's getting attacked first. So acid chlorides are much more reactive than the primary chloride there. So we definitely want to do the acid chloride attack before we do the SN2 attack. That's really what you want to do there. Let's see. Yeah. And that's everything I have to say on this side. So let's just keep going. We got a ton more to do here. Here is another fun reaction diagram. Don't you guys love these? Like I said, for the ester one, definitely go through Dr. Hossain's lecture. Watch him explain this step by step. Understand what's happening, please. Okay. This is really, really vital to doing well with this. And things like that. So we do have a bunch of reactants here. As you could tell, you have your alpha chloral 2,6 di whatever, toluene. This guy is your diethyl amine. If you notice in the actual reaction for this guy, you actually use 3 moles of diethyl amine. And we're going to talk about why in a moment, but just keep in mind that we actually use 3 moles for every one. So we use excess of that in this reaction, okay? And that's going to be very key in a moment. So here we have toluene and water. In your toluene layer, you're going to have these guys as well as a little bit of C. C also kind of goes into the water layer, and the protonated form of it will also go into the water layer or the aqueous layer. Then you add HCl. The purpose of the HCl is to then have English, A and C react with each other. Am I saying that? No. What am I saying, guys? B and C. Reset. Sorry, I think my brain is officially mush. Any leftover C could potentially react with B in this step. So that's why we add our HCl there. It'll eat away at any remaining diethylamine. Okay, so the point of the HCl, it'll eat away at any leftover diethylamine, eat it all up. Then we go ahead and we get B here, as well as the protonated form of lidocaine. Then we take what's in that aqueous layer, right? So the toluene, that's your organic layer, and the aqueous layer, that's what's going to have the protonated form of your lidocaine. So you take that, and then you used your NaOH, sodium hydroxide, right? You put drops of that in at a time, gave it a mix, it turned really white. Then you put it in ice, and you start to see crystals precipitate out of solution. So that was, in fact, your lidocaine, okay? I think because this experiment is more recent, it makes more sense, and it sticks a bit better. But in terms of the pathway that you guys followed to get to lidocaine, it's going to be this one here. Okay. All right. Let's do some questions. Why is excess diethylamine used in the lidocaine experiment? This was from your lecture, so I definitely wanted to go over it just a bit. So we used excess diethylamine. Like I said, we used 3 moles for every 1 mole of the other. The reason we use this is we need the excess base to neutralize HCl and prevent multiple alkylations. Okay, so there's 2 reasons. The first is to neutralize HCl. The second is to prevent multiple alkylations. Okay, the other question you want to ask yourself is, why did we wash 4 different times with 50 mLs of water? Why couldn't we just wash with all 200 mLs in one shot? The more common sense reason is just the sep funnel is not big enough to accommodate over 200 mLs of liquid, right? Your separatory funnels are pretty small. But the real better answer here is that toluene layer, right? If we look back really quick, that toluene layer, it's going to have some of what we want. So when we wash it with water, we're going to get out all of those impurities. Okay, so the more washes, the more impurities you can get rid of. Not get rid of, the more impurities you can extract. Okay, so the more washes, the more impurities that you can extract. Okay, everybody good there? Okay, now we have the fun stuff. I think I have 3 of these. Yeah, we have 3 mathy math questions to end it off. Like I said, I do not see your theory quiz ahead of time, nor would I want to. But if I were to guess, I would say you're definitely going to have one of these suckers on there. It was covered in lecture. He did about 3 or 4 of these in one lecture with you with the math. And then he also did like another 1 or 2 in the review. So I would definitely count on there being at least one of these guys on there. That's why I have 3 of them. I want to make sure we understand them, front, back, left, sideways, all of it. Okay, so this is the partition coefficient. So we're going to do this one together. Okay, it says, during the extraction procedure for the lidocaine experiment, the procedure acts to extract the toluene layer 4 times with 50 mLs of water, which would leave 2% of diethylamine dissolved in toluene. Crystal, however, thought it was wiser to save time and wash the toluene layer with 200 mLs of water. Assuming that Crystal had 5 grams of diethylamine in 50 mLs of toluene that she extracted with 200 mLs of water, what percent of diethylamine would remain in toluene, keeping in mind that K is equal to C toluene over C water, which is equal to 0.667. That is a lot of numbers. You guys see all the numbers in this question? I wish that's what my bank account would like add up to. That many decimal places. Like if we could just take them and smush them all together, right? Wouldn't that be great? That'd be wonderful. There's a lot of flipping numbers here. So let's kind of sort through the garbage and let's isolate the stuff that we need, okay? You see this whole beginning part where he's like, this is what should have happened, right? You see that? Well, we don't care about that. That's not what happened. That's what should have happened. That's great. Thank you for telling me what should have happened, because maybe in the theory quiz, in another question, that will give me the answer to something else, right? Make sure you're using the theory quiz to take the quiz. Anyways, so Crystal thought it was wiser to save time. Let's just kind of talk about what the partition coefficient is. So with the partition coefficient, we can say that K is equal to the concentration of toluene all over the concentration of water. Okay, that's great. So K is the partition coefficient, and then we have the concentration of toluene over the concentration of water. Okay, concentration of toluene. The way you decide C of T, you do grams over mLs in toluene. Concentration of water is equal to grams all over mLs of water. That makes sense? That's the part they don't tell you. They have to like figure out for yourself. So we need to essentially fill this in. Okay, so if I were to fill it in with the information I have right now, I have the partition coefficient, which they do tell us. It's kind of sneaky, but K is equal to 0.667. Look at that sucker. So we have K is 0.667, which is equal to the concentration of toluene. Well, we have grams, right? What do we have grams of? Well, we're dealing with, in this case, grams of diethylamine, right? So we want to know altogether the percent of diethylamine in toluene. So because we want to know the percent of diethylamine in toluene, that's going to be our X. We want to solve for how many grams will we have left over in toluene. How many mLs of toluene do we have? We have 50. So we have X over 50. That's the concentration of toluene. Then you divide that entire thing by the concentration of water. Well, how much diethylamine is in water? We have no idea, right? We know that 5 grams of diethylamine is in 50 mLs of toluene, which was extracted with water. So the way you set this up is you say, okay, 5 grams minus X all over the amount of water we had, which is 200. And now you solve. Does everybody understand this setup? How we got here? Okay, cool. So now we math it. Here's how you math this thing, because this is a monster, and I don't know about you, but I don't do math this well. So you take this whole bottom piece, multiply it on both sides. All right, we're gonna do some operation here. Orders of operation. So we're gonna multiply this by 5 minus X over 200. And then same thing, we're gonna multiply this by 5 minus X over 200. And what that will do is that will cross these out. Magical, right? So then we get something that looks like this. I should have gave myself more room. We get 5 minus X times 0.667 all over 200 is equal to X over 50. And now I'm somehow back in high school math and I want to cry because I have to solve for x. Okay. So let's keep going on this roller coaster here. Well, we need to get x by itself, right? So now what we're going to do is we're going to multiply by 50 on both sides to get rid of the 50. You might think it's silly that I'm explaining it like this, but if we're being honest here, it took me longer to figure out how to do the math than how to set it up when I was practicing these earlier. So just if that's you right now, you're not alone, okay? So we're multiplying by 50. So what we're really doing is we're doing 50 divided by 200. If you do 50 divided by 200, you are going to get in your calculator most likely 0.25. Please do not mess it up because I did. What it really means is you're doing, the big number stays on the bottom. So you're doing 5 minus x times 0.667 over 4. 0.25 in fraction is 1/4. So you're really getting 1/4. Okay. Now, if I seem like a complete buffoon to you right now, honestly, it is what it is. I know how to teach it at the moment, which is great. So if you know this math better than me, kudos, but I'm struggling, guys. Now, just solve as is, okay? So all we're doing is we're doing the order of operations. So we do 5 times 0.667 and then x times 0.667. So now, we move that up. 5 times 0.667 is 3.34 minus 0.667x divided by 4, which is equal to x. Then you multiply 4 to both sides. So then 3.34 minus 0.667x is equal to 4x. You add 0.667 to the other side. I'm going to make this smaller just so I have more room to write for you guys. Okay. I mean, if I were to give this on an exam, I could see this easily being what? Like 6 to 8 points, you guys think? I could see 6 to 8 points on this. So then we add, right? You combine like terms plus 0.667x. Once again, I'm showing it all out just so that if you're a bit confused, you see what's going on here. Divide 4.667, divide 4.667. What do you get for x? You get 0.715 grams. Okay. Did they want grams? No, of course not. Right? So if you get this far, you haven't finished the problem, so please do not move on. So we want the percentage of diethylamine that remains in toluene. We have the mass, we have the grams. How do we then convert this into a percent? We do 0.715 grams, divide it by the 5 grams that we know we have, and then multiply by 100. So it's 0.715 over 5 times 100. So you should get 14.3%, or if you want to use your sig figs, you could do 14, which is probably the better number here because it's less sig figs, right? More accurate. So 14% is the correct answer for this question. Like I said, I'm thinking if this is on your theory quiz, definitely a 6 to 8 pointer. Okay, there's a lot of work involved in this, I personally think. Everybody good here? Okay, let's do the next one. So now we are going to assume that we have 10 grams of diethylamine and 50 mLs of toluene, and we're extracting that with 50 mLs of water. How much diethylamine will remain in toluene after the first extraction? And go ahead and put this in a percent as well. So this one I want you to try out on your own. Okay, using what we did on the last one, try to set this up just about the exact same way, okay? When you guys finish this one, feel free to hop onto the last problem as well, okay? Okay, awesome. So you guys are getting the answer. So let me run through it then. So I have it set up a bit here, right? So let's just quickly run through this, multiply on each side. So we go 10 minus x over 50. Cross that out. 10 minus x over 50. This one was nice because the 50s cancel. So it definitely does make it a bit simpler. And then you multiply both sides, you do all the good stuff. Ultimately, what it comes down to, or you know what, I'll just write it all out. Why not? It doesn't hurt. So these guys also cancel out. So then it becomes 10 minus x times 0.667 equals x. So then it's 10. Yeah. 6.667 minus 0.667x, and that's equal to x. So you should get, after you do some math, x is equal to 4 grams, and then you do 4 divided by 10 times 100. So your total should be 40%. Very nice job. All right, so you guys are getting the hang of these, which is flipping amazing. Because honestly, if you could at least, get these 8 points, like guaranteed on your theory quiz, 6 points, if it's even on there, which it probably will be, because, these are fun. That's great. So really strive for these points. All right. This one I'm going to set up as well, and then we'll go through it once you guys start giving me some answers, okay? So we get K is CT over C water. So we have 0.10 is equal to the concentration of toluene, which is X over 100 all over 5 minus X over 150. All right, so you guys have to math it. All right, so let me know when you get this X value. Right, so after we math, X should be 0.31. However, in this question, you have to read it very carefully. It changes ever so slightly. It's asking for the percent of a solute removed from 100 mLs of toluene. In the previous questions, we were asked for the percent remaining. So be very careful. So if you need percent remaining, you're going to go ahead, take your value, divide by the total number of grams, times it by 100. However, here we want the percent removed from toluene. So the percent removed would actually be 5 minus 0.31, right? We're getting the percent removed. So 5 minus 0.31, which gets you 4.69. And then you divide that by 5. So it's 4.69 grams removed from toluene. So anything removed from toluene goes into water. So here we get 94% has been removed from toluene. Okay. So I wanted to give this one just because it shows the other way they could ask it. So when you're reading, just make sure you know if they're asking if it's being removed or if it's remaining. Okay, because that will change up how you calculate the final answer, depending on what they're asking. Alrighty, guys. I mean, this went over an hour and a half, which I was expecting it to. So it's about 2 hours long total, which isn't too bad. This is everything I have for you guys. I really hope it helped. I wish you all the very best of luck on your theory quiz. If you're looking for the recording of this, it's going to be at that link there. Okay, I'm also going to post this on Blackboard for you guys. I really do wish you all the best of luck on Monday. Kick some butt. Okay, do your very best. I'll bring some candy for the end. So if I happen to be in your room, you know, and you want some chocolate or something. All right, guys. Enjoy the rest of your night and enjoy this weekend. All right. Good night, everybody. Bye.